All right, so last week we looked at our first limits and we saw how those can at first come up, but in those cases you're given a graph and you're asked to figure out what the limits would be from the graph. Here you're being asked to go backwards and actually make a graph that satisfies these requirements. And it can be a little bit tricky. Now there's different ways that people go about it. Some of you, I know you're just going to look at this and you're going to start by kind of mentally doing it all in your head, where you're going to say, okay, I'm looking at a limit where as x approaches 0, 3 from the left, 3 from the right, and then the value at 0. And so those are the areas I'm going to focus. So how do I make some of those things happen? And if you're doing that, kind of doing the pre-thinking, that's fine. But I'm going to show how could you do it if you're not seeing it that way. Just because I kind of want to lead you through a process. All right, so the first thing that I'm going to deal with is just this. I want the limit as x approaches 0, and notice that's not from the left or the right, that is actually from both sides. I want the limit as x approaches 0 to be 1. So then that means that at 0 here, that I should be going through 1. That's what that's telling me at the moment. Because that has a limit of 1. All right, next up, I'm going to go over here. As x approaches 3 from the left side, I should be approaching -2. So I'm going to go down to -2 and 3. So I'm going to go right down to that point right here. And I want to be approaching that point from the left. Now, does it matter if I'm going like that, or if I'm going like this, or if I'm going like this? Does that change any of that? No. I'm still approaching -2 from the left. And so it doesn't matter which way you do it. I'm just going to do it like this. Okay? All right, then the limit as x approaches 3 from the right. Wait, I did something wrong there. What did I do wrong? Yeah, I put it -3. When I saw this, I was thinking -3, but it's not -3, it's +3 from the left. So I need to go over to +3, and I need to be hitting -2. I need to be doing one of those. So I need to be approaching this point from the left. Now, if I'm going to approach that point from the left, I'm going to kind of try to connect it up with what I already drew. So I'm going to try to maybe connect that there. Okay. Now I can go on to this next one. The limit as x approaches 3 from the right. Should be up at 2. So that means that if I'm coming at it from the right side here, I should be approaching 2 at 3. So I go over to 3, I go up to 2, and the graph is going somewhere to the right from there. All I need is that if I'm following this graph from the right-hand side here, I should be getting a limit of 2 as I hit 3 there. And so it doesn't matter if I'm doing that current curve that you see there, or I could also be doing this, or just this. It doesn't matter as long as I'm approaching that same thing. So it's kind of just whatever you feel like doing there. All right, so I'll just do that. All right, and then the last thing is we need f of 0 to equal -1. Well, notice that f of 0, I already have it up at 1 here. So how could I possibly have it also having an actual value at -1? Yeah, it means that we got to put an open circle up there where we're getting our limit. So I got to put an open circle up at 1. So I'm going to erase that, erase a little spot, and put the open circle in up there. That way I can put the solid dot down at -1. All right, and so now I can get a lot more picture of the graph. To the left of 0, it doesn't matter what I'm doing as long as I'm still approaching 1 from the left. And so it could be doing anything over there that you want it to. And this is looking pretty good, but there's still one little detail that's slightly off. One tiny little thing that we're going to need to tweak here. Yeah, we currently have 2 solid dots here at 3. What tells us that we can't have that? Well, notice we're using function notation here. And so this thing needs to be a function. So, option 1, erase both of those and make them both open circles. But do I have to do that? Could I make the top one solid? Would that be okay? Would that still work? Yes, that would still work. There's nothing that told us that that had to be one way or the other there. Could I make the bottom one solid? Yes, because it's still a function. Could I make both the top and the bottom solid though? No. We cannot do that, again, because then it's not a function. And so any combination, we have a little bit of freedom of choice in there. A follow-up question. Is there a way that you could have built this so that the limit as x approaches 3 of f of x equaled some value? Like let's say it equaled 2. Could you build this so that that would happen? Well, this one's a little bit tricky. I'm bringing it back to help refresh our memory about stuff we saw last week. In order for the limit at 3 to exist like this, remember that that means that the limit from the left and the right must be the same. So in order for the limit at 3 to exist, the limit from the left and from the right must be the same thing. Are they the same here? No. And for that reason, it would actually be impossible for us to create a scenario where the limit at 3 equaled anything. It would always have to be does not exist, just inherently for that. That's also why, by the way, as we do the limit as x is approaching 0 here, why we have to be approaching 1 from both sides. You couldn't just have one of those. You have to have it coming into 1 there from both sides. Now, we don't want to always have to be dealing with just graphs when it comes to limits. In fact, graphs is a great way to kind of visualize what's happening at the start, but the most common way you'll be dealing with limits is actually algebraically. So today is going to be all about how we can find those limits algebraically. And the first method is just direct substitution. This is a great thing to put into your notes. We're actually going to have a grand total of 4 different methods. We're just going to take them piece by piece as we go. Only 2 of them today. But go ahead and write this one down. All right, now you'll notice that direct substitution, we'll see how we're actually using it, but basically it just means plug the number in. We have some details here about how it works with polynomial, rational, root equations. There's even others, like it can work with trigonometric, it can work with all sorts of different equations. Notice a little detail here. The root, except at the endpoint. Why would a root, like a square root, not work at the endpoint? So like, you know, if you make a graph of square root, it has an endpoint here. Why could we not find the value there? Like let's say that this point's at 2 here. Why could we not just plug into the limit as x approaches 2 of our function? Yeah, it has to come from both sides, remember. If I were looking at that point, I could know the value, the limit as we approach it from the right, but we could not know the limit as we approach it from the left, because there is nothing to the left to use to approach. And so that's why we have that one little caveat in on that one. And then you notice it says for all values in the domain. And that's going to be an important factor there. So in other words, if you plug it in and there is no value, like you get DNE when you try plugging this thing into the equation, like if you're doing square root of x and you try plugging in -1, that's not going to work, right? Because -1 is not in the domain. It will give no value, and therefore it will not help us find the limit. That's all that's really talking about there. I want to practice this idea with this particular limit. And when we talk about finding this limit by direct substitution, what we're literally going to do is we are going to plug the 3 in for x. So we're going to do 2 times 3 squared plus 3 times 3 plus 5. Notice the detail here. When I plugged the x value in, I'm no longer writing limit next to it. Because this limit up here is saying I will find the limit of the expression. When I plug the 3 in, I am actually finding what the limit is. And so I need to get rid of the limit notation because I'm now calculating the actual value. And so now it's just a matter of actually doing that calculation. So 2 times 3 squared, of course that would be 2 times 9, so that's going to be 18. Plus 9 plus 5. When you do that, you should be getting an answer of 32. And so we can find then that as x is approaching 3 in this polynomial, we would find that we are approaching it from both the left and the right at a height of 32. That's what we're able to find out. Very simple, straightforward with direct substitution. Okay, but we will see that things are going to get a little bit trickier. Before we get too tricky though, let's go ahead and do these two. Please evaluate both of these limits on your own first. And so for that first one, this is what your first step would be looking like. You're just taking the -1 and you're plugging it in for x. And again, you are not writing limit next to this once you plug a number in for x. That is the point at which the limit notation goes away. And so when you work that first one through, you end up with 0 over -8. Can we do that? Can we do 0 divided by a number? Yes, we can. If you have nothing and you share it with 8 of your friends, everybody gets an equal slice of nothing. We can do that. You just can't take your apple and divide it up into 0 pieces. You'll always have some pieces. So it's dividing by 0 that you can't do that. But 0 on top, that's okay. And then for the second one, you should get an answer of just 2. So in that case, as the limit is x is approaching 1, we are approaching a y value of 2 from both sides. And notice it was not at an endpoint, so we could go ahead and get away with it. Now, if I had asked for what's the value as the limit of x approaches -3 here, that would have been a bit more of a problem. We could have plugged it in, but it actually would not have been the limit because we would be at the endpoint. So that's the one thing to try to remember anytime you see a radical in there. All right, now please evaluate this limit. All right, so this one, when we work it through, we end up getting 0 over 0. Well, a 0 on top we can do. A 0 on bottom we cannot do. What if they're both zeros? Can we do it? Nope. The trump card is the one that we cannot do. The 0 on bottom, we don't even need to know what's on top. There is no exception. The 0 on top will always equal 0 unless there's a 0 on the bottom. And so there actually is no solution for this one. There is no value. This particular example here, we actually are evaluating it at an x value of -1, which is not in the domain then. That's what this is telling us, is that -1 is not in this particular equation's domain. So then, how can we deal with it? Well, there is a way. And if we were thinking about the graph of this, what is actually happening in the graph of this function at x equals -1? Would this actually be an asymptote? Or would there be a hole here at -1? All right, so we could say it's a hole because the restriction on the bottom is the -1. And that's going to work. How else could you get this? You could actually break out your calculator and graph it. Another way is that you could actually do the simplifying and see what that leaves you with and see if that gives you something where there's an asymptote at -1. But yes, there is a hole here. Now that actually means then that if I were looking at the graph, we can do this then, because wherever that hole is, it's still going to be approaching that from both sides. So we could still find the limit. So in order to do so, what we're going to do is we are going to factor and then cancel. In other words, simplify the rational expression, and then we can use that to find the limit. So step 1, please factor the quadratic on the top here, and then simplify your rational expression. All right, so we know that we're going to end up with something that looks like this. We just need to then figure out what two numbers add to 4 and multiply to 3. Well, there's only one way to multiply to 3, and that's 3 times 1. And yes, that does add to 4. So that works. Now, notice that when I wrote this line, I included the limit. Why am I still writing limit here? Because I still have the x's here. I can only get rid of the limit as x approaches -1 when I get rid of the x's themselves. All right, so now that I've done that, I can now do the canceling part, and you notice those x plus 1s are going to cancel each other out, which then leaves us with finding the limit as x approaches -1 of just x plus 3. All right, now that we simplified what we started with, now try direct substitution again. So now try plugging that -1 in and see what we get. Notice, -1 plus 3, that's doable. And so by simplifying this, we were able to figure out what's it approaching. And we found out that it was approaching 2. So that is our actual solution. We can know then that we do have a hole here, but that hole is going to be at a height of 2. You can't find it out just by plugging in directly, but if you simplify first, you can get there. And that's what all these other techniques that we look at are going to be all about. It's going to be all about manipulating our expression, often by just simplifying it in some way, in order to be able to then try plugging it in and get something different. Now that means that this is our second method. The first method was just direct substitution. The second method is factor and cancel. So go ahead and now add this to your notes where you wrote the first one. Again, remembering that we're going to have a total of 4 options by the time all is said and done in the next couple of days. And now that you got these in your notes, I want you to practice one of these on your own. So please evaluate this limit. Now in doing this, I hope the very first thing you did is at least check to see if you could just do direct substitution. It makes sense, since we're just talking about factor and cancel, that we're probably going to have to do factor and cancel, but make a habit of always checking direct substitution first. But in this case, yes, if I plug the 5 in, 5 cubed is 125. That would give me a 0 on the bottom, so yes, we do have to factor and cancel. Which means, yes, you also have to remember how to factor the difference of cubes. Right, so when you factor the difference of cubes on the bottom, this is what you should be looking at. Now, if you're a little rusty on that, scrape some of that rust off. This is still a skill you're going to need. It's going to come up here and there, often enough where you need to know it. But now that we're to this point, go ahead and proceed from there. All right, so we go ahead and we cancel out those x minus 5s, since we do have that same factor on the top and bottom. Now that we've done that, now we can go ahead and plug in the 5. Plugging in the 5 means that means the limit notation now goes away. So we're just going to be doing 5 squared plus 5 times 5 plus 25 on the bottom. And so that's 25 plus 25 plus 25. So that'd be 75. So we end up with a grand total of 4 over 75 as our final answer. And yes, oftentimes you will end up with some fractions that are kind of finicky looking. But that's actually kind of helpful for us to know, because this certainly is not the value where if we sketch the graph that we'd be able to come up with that, right? We aren't going to be able to tell that it's at exactly 4/75. That's one of the things that finding these limits algebraically is going to allow us to do. Is it allows us to find values that we would not have been able to find otherwise.